Now on to section B. First, nuclear reactors. Now, in order to use uranium in a nuclear reactor, first we need to increase the concentration of the fissile isotope, that's uranium-235. The process we do this by is called enrichment. Now, we need to do a calculation. How much uranium do we need in a reactor to produce a certain amount of energy? Now, several ways we could go about this. I'm going to go about this first by saying how much energy do we need to generate in 1 year? Now, we know that the power produced is 24 megawatts. So that power needs to be sustained over all of the seconds in a year. So the power in joules produced per, the energy in joules produced per year is going to be that 24 megawatts times 365 times 24 times 60 times 60. Well, that's only the useful energy output. However, the reactor is only 32% efficient. So in order to produce that much useful energy, we actually need to produce even more, we actually need to use even more uranium. In fact, we need to divide that by the 32% to find the total amount of uranium required. So that comes to an amount in joules per year. The amount is 2.36 times 10 to the 15 joules. Now, we know how much energy is produced in one fission of one uranium nucleus. So the next question is, how many uranium nuclei do we require? The number of uranium nuclei we need is just going to be the total amount of energy we need, 2.36 times 10 to the 15, divided by the energy we get from one fission. This is going to give us a huge amount of fission events. That is 7.4 times 10 to the 25. Now, what's the mass of this many uranium nuclei? Well, first we could say that 1 mole of uranium-235 has a mass of 235 grams. And then if we convert the number of uranium nuclei into moles, then we can transfer that back to a mass. So how many moles is this many nuclei? Well, if we divide this number by Avogadro's constant, that's 6.02 times 10 to the 23, it gives us a number of moles. 123 moles. So therefore the mass of uranium required will be the mass of 123 moles. That's 123 times 235 grams, or if we want an answer in kilograms, 0.235 kilograms. The final answer is 28.9 kilograms, or two significant figures, 29 kilograms. Next, we need to explain what would happen if the moderator were removed. To do that, we need to understand the function of the moderator. The moderator is a substance that's included in the core of the reaction vessel to slow down the neutrons. And the reason we need to slow down the neutrons is because if they're moving too quickly, they're not going to be absorbed by other uranium nuclei, and the reaction is not going to continue. So the moderator is necessary to allow the reaction to continue. So, to get 3 marks, what do we need to say? Well, here's the mark scheme answer. Firstly, we need to say, if we remove the moderator, the neutrons would not be slowed down. And because they're not slowed down, they're not going to be captured by other uranium nuclei, they're not going to induce fission, and therefore the reactor would either stop producing power or less power would be produced. Now, a certain set of reactions taking place. The uranium-238 turns into 239, that then decays into neptunium, then the neptunium decays into plutonium. Now, what's the process represented by reaction 2? Well, if we look at this reaction, what's being produced, we should be able to recognize this, an electron, as being a beta particle. So this, in fact, is beta decay. And so in fact is step 3. Next, comment on the international implications of the product of these reactions. Well, what's the product? The final product is this one, plutonium-239. In the news a lot because one major international implication is the use of plutonium in nuclear weapons. So 2 marks here, one for identifying plutonium as the product, and secondly for commenting on nuclear weapons. In part 2, we're looking at simple harmonic motion. Here's the displacement time graph for a particle executing simple harmonic motion. First, how can we see that these oscillations are not damped? Well, damped oscillations are oscillations where there's a resistive force that's reducing the amplitude of the motion. But we can see here, at the beginning, the peak here, the maximum displacement of the particle is 2 centimeters, and 1 cycle later, it's still 2 centimeters. The amplitude is not changing. So that's our answer. Now, to calculate the magnitude of the maximum acceleration. Well, we have a displacement time graph, and if we know the relationship between acceleration and displacement in simple harmonic motion, we should be able to find the acceleration. So the relationship is the acceleration is minus omega squared x, where x is the angular frequency. So let's find the angular frequency in this motion. Omega is 2 pi over t, where t is the period. And going back to the graph, we can see the period, well, from one peak to the next peak, is 0.2 seconds. So 2 pi over 0.2 is 31.4 units per second. Now, we want to find the maximum acceleration. To find the maximum acceleration, we need to look at when the displacement is also a maximum. So the maximum displacement is 2 centimeters. So our maximum acceleration is going to be equal to minus, or because we're just looking for the magnitude, let's ignore the minus sign, omega squared, so that's going to be 31.4 squared times 2 centimetres. Let's just remember we're dealing in centimetres here, not in SI units. So work it out. We get quite a large number in centimetres, so I'm going to convert this then to metres. So centimetres per second squared. And I'm going to give my final answer in metres per second squared, so just write it down in centimetres per second squared first. 19.7 metres per second squared. Now, I need to find the speed at t equals 0.12 seconds. So let's look at what's happening at 0.12 seconds. That's this time here. This is neither the end nor it's neither the maximum displacement nor the zero displacement point, so it's not going to be an easy calculation. But we can do it. Let's read off the displacement of the particle at this time. It is minus 1.56, nearly 7. Let's say approximately minus 1.67 centimeters. So what's the relationship between displacement and velocity? Well, there's an equation from the data booklet. We just plug in the numbers. So maximum displacement is 2. And the answer, again in centimetres per second, is 34.6. And the direction of motion at that time. Well, we can see the particle is returning from its maximum leftward displacement back towards the right. So it's moving towards the right. Now here's a second graph. And this one's not a displacement time graph, this is a displacement distance graph. It's a snapshot of the wave at a particular moment in time. So from this graph, or from the two graphs, first we need to find the frequency. We can't find the frequency from this graph because there's nothing to do with time on this graph. Back to the first graph. Well, the first graph, the period was 0.2, so frequency is 1 over the period, so 1 over 0.2 is 5 Hertz. And speed, well, in order to find the speed, we can use V equals F lambda. And we know the frequency is 5 Hertz. The wavelength we can read off the second graph. The wavelength from here to the same point on the next wave is 16 centimeters. So 5 times 16 gives us 80 centimeters per second, or 0.8 meters per second. Now here's graph 2 again to help us with the next part of the question. Now, the second diagram here shows 6 particles in their equilibrium positions. And we want to show the displacement the positions of these particles when their displacement is as shown in the first graph. So, if we look at the first particle, here's the first particle. On the graph we can see this one has 0 displacement. So 0 displacement is still going to be here. So we leave it there. And we're marking a cross on this position to indicate that it's still here. Now the next particle that would normally be at 4 centimeters, has been displaced 2 centimeters to the right. So 2 centimeters to the right takes it here. The next particle at 8 centimeters, 0 displacement. 12 centimeters is displaced 2 centimeters to the left, so that takes it to 10 centimeters. 16 centimeters, 0 displacement. And at 20 centimeters, displaced 2 centimeters to the right, so that's at 22 centimeters. And now we want to label a particle that's at the centre of a compression. Well, compression is where the particles are more tightly packed than they would normally be. They're closer together than normal, and we can see here we have 3 particles that are closer together than they would normally be. And the axis of symmetry is about this particle here at 8 centimeters. So the centre of the compression is at 8 centimeters.